First thing that I've forgotten over the last couple of days, after today's lecture, there's some stickers, some Penny Lane stickers, some Xanadu stickers, and a sort of postcard of stickers that each one of you can pick up as a sort of gift for participating in this school. So today we're going to keep going on our exploration of applications of quantum computing to quantum chemistry. Last time we saw, building up on the first lecture, that we looked at VQE as a very simple example of a quantum algorithm, a near-term or a NISQ quantum algorithm. We looked at the importance of initial state preparation. So if you have the resources to do better than Hartree-Fock, it can pay off quite a lot in both reducing the number of optimization steps that you can take, and for more complex problems, giving you a more accurate solution to your problem. And that's shown on the top right over there, where we saw that in the case of H3, it reduced the number of optimizations we needed. I forgot to mention, but if you go on the school website, under videos and files, over here for today's lecture, you have the solutions from Tuesday. So you can try it out. There was a little bit of problem with the initial state preparation demo. So you can see what it was actually supposed to look like. And you also have a notebook that we'll go through today on a different problem. So we also looked at a couple of very simple chemical reactions. We looked at the dissociation of H2 into 2 hydrogen atoms and calculated the dissociation energy, so how much energy you need to actually pull apart the 2 hydrogen atoms. And we also looked at a slightly more complicated reaction, the hydrogen exchange reaction, where you have just a hydrogen molecule next to a hydrogen atom, and you pull one of them apart until it attaches to the other one. We looked at the idea of transition state and activation energy and the effects that temperature has on reaction rates and the importance of very precise computations. I don't think I emphasized that enough yesterday, but if you do a computation and you go tell an experimentalist, I would expect your reaction to take this much time, and it takes 50 times less. It could make a very important difference. It could make a very dangerous difference. If you have an exothermic reaction that's supposed to take an hour according to a computation, but it takes 1 minute in reality, that difference in time scale is big, especially for an exothermic reaction. You can have an explosion rather than a controlled release of heat, for example. So we then have time to go through Penny Lane data sets. So we'll start off with that today. And then we're going to continue our exploration of algorithms for energy estimation, but we're going to go beyond the ground state energy. VQE is by far not the only algorithm that exists for ground state energy estimation, nor is it the best one necessarily. There's also interest in kind of low energy states that we'll look at. We'll look at one particular variation algorithm as an example of that. And of course, there are lots of other ones that you can look at. And then we're going to end today with a look ahead beyond NISQ algorithms. So start looking at something that at Xanadu we call intermediate scale quantum algorithms. This is when you start being able to use a few logical qubits, so qubits that are protected from error, and a little on resource estimation. So if there are algorithms that exist that allow you to estimate how many qubits and how many gates you're going to need to run an algorithm up to a given precision without actually running the algorithm itself. So I talked about Penny Lane datasets a little bit yesterday very briefly. These are databases that are hosted on Penny Lane with ready-to-use datasets of various molecules and various spin systems, and in some cases, machine learning data sets. What this looks like for the case of chemical data sets, if you go into the page, is something like this. You have a range of different molecules that, by and large, at the moment, people at Xanadu have done the computations for things like ground state energy, dipole moment, the full configuration energy. We're going to see that you even have, for example, data on optimized variational circuits, so you can get optimized gate parameters for VQE, for example, so that you don't actually have to run or do the things we've spent the last couple of days doing. For some cases, you have ready-to-use data that you can build off of. So they're organized kind of by how many resources you need, how many qubits you need. For small molecules, of course, it doesn't matter. You're welcome to do this yourself, but you can see that you have a variety of parameters that you can choose from. In this case, you can, for H2, it's showing that you can change the bond length, so something similar to what we did yesterday. You can also choose the basis set that you're choosing to represent your Hamiltonian in, or your wave function in, sorry. The STO3G is kind of like the minimal basis set, so it's uses the least amount of resources, but of course that means that you have less precision. You can use a bigger basis at the cost of more computational power, but also higher precision. Okay, you have a few other attributes that are shown here, so dipole moment, the spectrum, obvious quantities like the Hamiltonian, the molecule that we looked at. So we're going to spend maybe like 5 minutes just briefly looking at how these data sets work, because we're going to use them today and tomorrow to minimize the amount of work that we have to do. All right, so let's try this out. So if you go to, if you download today's notebook from the school website, you should get something that looks like this. So as always, we start by installing Penny Lane in the servers that we're accessing and importing the libraries that we're going to need. This will take a little bit. Okay. So the example we're going to look at is we're going to load the data set for H3 and access things like the Hamiltonian, the VQE gates, the optimized VQE gates, and you can get like the ground state energy, for example. So oops. So if you want to load a given data set, Penny Lane has a built-in module called data, and then we're going to load one of the quantum chemistry data sets. In this case, we're going to get the data set for the H3 ion. And this normally gives you an array. We only need the first element of that. You can see here in the next one, we're going to get the Hamiltonian. We're not recomputing the Hamiltonian like we did in the past. We're actually just accessing it directly from this data set. Okay, so you can see already for the H3 ion, it's a very complicated Hamiltonian in the Jordan-Wigner mapping. This is about 66 terms, if I remember correctly. More zoom? Yes. Good. Yes. Of of lights. I don't actually know how, if you can even have access to these. Let me see. Good. Okay. Okay. So you can see this is a huge Hamiltonian, and this kind of speaks towards what we're going to talk about at the end of the lecture. If you think this is big for molecules of industrial interest or useful cases, you're going to have Hamiltonians with millions of terms in them. So you can see that the scale of the problem really gets quite big really quickly. If you can do what? Yeah, so I didn't specify the length of the bonds. By default, it takes the equilibrium ones, but you can change its parameters that you have access to that you can change. So we're going to need the number of qubits, which we'll call number of wires here. So that is a built-in property of the Hamiltonian. And it normally doesn't take so long. Yeah, so you can see we have 6 qubits, as we saw yesterday. If you want, you can also just run this again. You can see the Hamiltonian does indeed have 66 terms in this case. So we don't need to, but just for the sake of showing you how you can use this to speed up your process, we're going to do VQE very quickly by loading directly the pre-optimized Givens rotations for this data set. So as always, we first define a device. We're going to encode the initial state. These data sets typically have the Hartree-Fock state preloaded into them. And we encode these over the 6 qubits that we have. To apply the VQE gates, we're going to loop over the gates that are stored in this particular data set. And we'll return the expectation value. So we're pretending like we're trying to estimate the ground state energy. Okay, and to give you an idea what this will look like, or of what the optimized circuit looks like. Okay, so if you remember, if I just zoom out for a moment, Tuesday, when we looked at the H3 ion, we took all possible singles and doubles excitations, just as a brute force approach. Whoever built this data set did a different method where they found that the single excitations actually don't contribute very much, so you don't need them. All you need is 2 double excitation gates to get a good enough estimate of the ground state energy. Yes. All right, any questions so far? So naturally, what this lets us do is, first of all, we don't need to actually run VQE for a lot of these molecules, at least for the ground state. And it gives you an idea, if, especially as you're learning, what other kinds of algorithms can you explore to try to match what's in the data sets. As I said yesterday, we took a brute force approach. We tried all possible singles and double excitations. It turns out you don't need to do that. You can explore algorithms that can demonstrate that you actually don't need all of those gates. So we can, in this case, we can get the ground state energy directly. Okay. You'll notice if you compare to what we did yesterday, sometimes you'll get a better estimate of energy in these data sets. It just means that they probably optimized other hyperparameters. They chose a different step size. They chose a different optimizer. You might be able to get better estimates than what's in the data sets. That's simply because these data sets are built up until you get to chemical accuracy. Once you get to chemical accuracy, you don't need to spend any more resources going beyond that. So we already saw this in the picture, but you can also access the gates and see what they look like. And you can see you have the 2 double excitation gates with their optimized parameters preloaded here. And you can actually access the parameters directly in this way. Okay, so far, nothing particularly exciting. It's going to help us in that we won't have to recompute certain things in the next couple of days. To give you a slightly more interesting example, we're going to look at the lithium hydride molecule. We're going to load the data set for that, and we're going to specify additional parameters. So we start the same. So we're going to specify the bond length this time. We want the data set of lithium hydride at a bond length of 1.57 atomic units. We can also specify the bases. So if we take something like a minimal basis set, that's the STO3G. STO3G, by the way, stands for Slater-type orbital with 3 Gaussians. And we can also, we don't need to load all of the data set. We can also specify which quantity we're interested in particular. Attributes. And in this case, we want the full configuration interaction energy, so the ground state energy of lithium hydride. Okay. And then we can print this out. Okay. And you can see without having to do any computations, we were able to get an estimate of the ground state energy of lithium hydride. So again, the idea here is reduce the time to research for whatever application you're interested in. In a lot of cases, the ground state energy, for example, has already been computed. Things like the dipole moment of a molecule may already have been computed. You can use that to build up on previous work and not reinvent the wheel for everything. And that's going to be important for us when we look at this variational quantum deflation algorithm for excited state energies that I'll spend some time explaining before going into the code. Any questions about the data set, by the way? It's fairly straightforward. It's really just not having to reinvent the wheel for certain applications. Yeah. Yeah. Yeah, there's like a dozen parameters you can specify. Yeah. It's penny lane data sets. So here, there's pennylane.ai/datasets, and you can get all the information there. Yeah. Okay, so the application we're going to look at today, as I mentioned, is going beyond ground state energy estimation. It's not the only problem of interest in quantum chemistry. We're also interested in a lot of other problems, one of them being excited state energies. As a simple example of this, if you want to learn something about the optical properties of a material or something, you often need to know the band gap energy or the spectral gap energy. So if you want to understand things like absorption, emission, this naturally leads to things like if you want to calculate the spectrum of a molecule, you can do it computationally. There is some benefit to having a computational model of the spectrum to know what to expect in an experiment. So, as I said, there are several algorithms to do this. One of the easier ones to understand is this variational quantum deflation algorithm, which, as the name implies, is still a variational algorithm. The basic idea here is actually quite simple. You start off with the fact that if you know the eigenstates of your Hamiltonian or some approximation of them, they should form a complete and orthonormal basis set. So you know that if you have a good estimate of the ground state, whatever state describes the next excited state has to be orthogonal to the previous one. So if you're able to somehow guess or make an educated guess of an excited state or the eigenstate of an excited state, the variational principle still applies. If you know, let's call it psi1 exactly, and you make some other guess, you're guaranteed to always be above the actual first excited state energy. So the idea then is to try to make or to come up with a way of making a good guess from the excited state using the knowledge you have about the ground state. And in practice, there are several ways of doing this. The most trivial one is doing something like a Gram-Schmidt method, where you can build out an orthonormal basis set. Another way of doing it is through variational algorithms, which again, you build up a circuit ansatz. The ansatz is always going to change depending on your problem. Along with that, a problem-specific cost function and a training procedure. So in our case, we're going to build on the knowledge that we have from VQE from ground states, which allowed us to build a decent estimate of a description of the ground state wave function. So get a good trial guess, optimize it, get some optimized parameters. If we want to build a state that is orthogonal to what we estimated for the ground state, what we can do is add a penalty to our cost function. So unfortunately, the laser seems to be out of batteries, but what we have is I'm calling the estimate for the ground state psi 0 tilde. Before the parameters are optimized, it depends on a set of parameters. Once they're optimized, I drop that theta. The psi tilde of theta is now your guess for the next excited state. So you again have the expectation value of the Hamiltonian, so you're trying to estimate the ground state energy. But you have an extra penalty term that's going to penalize the overlap between your guess of the excited state and the ground state. So the more overlap there is, the heavier the penalty, and you're trying to essentially project out any kind of overlap between the ground state and the excited state, variationally. So it's going to be part of our optimization routine. My question to you, and probably some of you know this, is how do you calculate that quantity, that overlap quantity with a quantum circuit? So expectation value is relatively easy. Does anyone know of a way of calculating this? Well, okay, so, sorry? Sorry, one more. No, because you're not calculating expectation value. There's no operator. So it's not a measurement. Isn't it what? It is, I guess, some kind of fidelity, but there's actually a very common subroutine called the swap test. If you've never seen the swap test, I would encourage you to try this out, maybe this afternoon if you want. Analyze the circuit, look at the states after each gate, and try to convince yourself that if you have two functions, phi and psi, and you run them through the circuit, and you measure the probability of your first qubit, so the qubit at the top being in state 0, that's related to the square modulus of the inner product, or the overlap between phi and psi. So put another way, if you isolate the quantity that we're interested in, it's something related to a probability of the first qubit being in state 0. One thing to keep in mind, and we'll see when we draw the circuit that we're going to make, is here phi and psi are represented as a single wire. Typically, you need multiple qubits to represent that state. So we're going to see that you actually need several swap gates in practice. Okay, so we'll try this out. It's going to be broken up over several steps. We are going to use the data sets to get an estimate for the ground state. We're going to build up an ansatz for the excited state. So one part of the circuit is going to go to estimating the expectation value of the Hamiltonian for the excited state. And another part of the circuit, which is going to be the swap test, is going to be to calculate the overlap that we're going to penalize. All right. So let's try this out. So we're going to do this for the H2 molecule. We're not going to redo VQE for this. Instead, we're going to just load the data for that. Okay, and then from there, we want to extract the Hamiltonian and the number of qubits that we need. We need the number of qubits to know how many qubits we're going to have in the device. So from the data set, we're going to obtain our ground state. So everything's already optimized for us. So we're going to start off with the Hartree-Fock state, and we're going to apply the operations of the optimized gates. Okay, so we just did the same thing we did at the very beginning. We just created an optimized estimate for the ground state. Okay, so if you want, you can run this, and you can see it's the same result that we got previously. It's actually a little bit different. If you look at the optimized gate parameters, you'll see that this data set actually has slightly more optimized parameters than we got on Monday. So once we have the ground state, we can go back to our cost function. So what we did so far is we got this quantity over here. We need a circuit that's going to build up our ansatz for the excited state. And this one, we're again going to take a brute force approach. So we're going to define all possible single and double excitations. This is actually quite long, so let me speed things up. Okay, out of all of the singles and doubles, we're going to break this up into just the specific wires that they'll be acting on. And I'll explain this in a moment. So once we have the singles and doubles, we're going to apply each one of them, taking as input different parameters. So each one of these singles and doubles is going to have a different parameter theta I. That's going to be applied over a set of gates to our Hartree-Fock state. So our Hartree-Fock state we know because we have 2 electrons, it's 1, 1, 0, 0. So the first orbital is fully occupied, the second one is empty. And then all the singles and doubles that we're going to apply are listed here. Okay. It'll become more clear once we visualize the circuit. You'll see all of the steps that we've taken. The last part we're going to do is build up the swap test circuit. I've already laid some of the groundwork here for you. Remember, we want the inner product of our ground state, our optimized ground state, and our excited state ansatz. So we load those two states. We've already computed, or we've defined functions to compute those. So all we have to do then is build up the circuit for the swap test. And if you remember, I don't have it here, but it looks something like this. So we need to apply, we need one extra qubit, the qubits that we need to specify the ground state, and the qubits that we need to specify the ansatz of the excited state. First thing we need to do is apply a Hadamard gate to our extra qubit, and then apply a series of controlled swap gates between the two states that we want to take the inner product of. So we apply a Hadamard gate to our extra qubit. We're going to apply a series of control swap gates. And I'll explain the syntax when we draw the circuit. And then we end with applying another Hadamard gate to our extra qubit at the top. Okay, and if everything worked well. Okay, so I'll give you a little bit of time for those of you that are following along just to finish the code, and then I'll show you the circuit. So what the circuit looks like, you can see we have our ancillary qubit that we're going to use for the swap test here. We have the qubits that are preparing our optimized ground state over here. So this is the Hartree-Fock state. We're applying the optimized double excitation gate that we saw on Monday. The next set of qubits is building our ansatz for the excited state. This double line here, it's nothing. It's really just a barrier to separate the two parts. So this is building up the states that we need. The swap test comes in the next part. So you can see this weird for loop that we did over here is performing a series of controlled swap gates between your ground state wave function and your excited state ansatz. So you do a series of control swap gates and then a final Hadamard test. And remember that the value of the overlap between the ground state and the excited state comes from the probability of measuring your ancillary qubit in state 0. So we only do a single measurement. We don't need to measure all of these other qubits. Okay, and just to give you an idea, if we just take a random set of parameters, you can see that we calculate an overlap of about 0.9. So a significant overlap. We're starting off pretty poorly with our guess of the excited state ansatz. It's pretty closely matching the ground state. Okay. So if we go back to our cost function, what we've done so far is build a circuit that's going to compute the second value. We need a circuit to also compute this value, this expectation value. And that's what we have over here. So in the interest of time, I've left it completed for you already. This one is calculating this first term, and then we're defining our loss function as the sum of the result of these two circuits that we just defined. Okay. And then you can run the optimization routine. And you can look at the details afterwards. You can see that we get an estimated energy of minus 0.53. And I want you to keep this number in mind, because what we're going to do now is solve the problem exactly. So diagonalize the Hamiltonian of the H2 molecule exactly and compare our result. It's one of the advantages of solving toy problems is that you can actually solve them exactly numerically and test your method. So for those of you that are familiar with Python, how do you think we can, how can we get the exact solution? Yeah, so we're just going to calculate the eigenvalues of the Hamiltonian. You can go back just to linear algebra. It's just a matrix. You're just getting the eigenvalues. And we're going to sort them in increasing order so we know which ones to compare. So we want the matrix representation of our Hamiltonian. Because the Hamiltonian is a Hermitian matrix, we know it's only going to have real values, so it helps in reading the values just to take the real part. We're not losing any information if we throw away the imaginary part. And hopefully this works. Okay. So I want you to compare the exact eigenvalues that we get from diagonalizing the Hamiltonian and our estimates for the ground state, which are is all the way over here, and the value that we estimated for the excited state. And I want you to tell me if you notice a problem. No, we're close enough for our purposes. Yeah. Yeah, if you look at the exact eigenvalues, there are degenerate values that are actually smaller than what we predicted. So what do you think is happening? So I'll give you a hint. Our estimated energy here is the correct one. We got the excited state of H2 correctly, the first excited state of H2. Yeah. It's somewhere close to that, I'd say. So what this is illustrating is the importance of the difference between physics and math. What we're doing by diagonalizing the Hamiltonian is we're ignoring the physics completely. what those two other eigenvalues represent is a state that has less electrons than we actually have. So if you look at the eigenstates corresponding to those two eigenvalues, you're going to find that they don't conserve the number of electrons. They might correspond to something like the 1,0,0,0 state or something. Whereas this one is the proper next highest eigenvalue that still preserves the number of particles in your problem. So whenever you do these types of computational estimates, it's important to keep in mind that you're looking at a real physical system that has limitations. It reduces kind of the space that you need to search in. And in some sense, it's also important to keep that in mind when you look at like complexity studies of algorithms. You'll usually see that looking for the ground state is computationally, even for a quantum computer, an impossible problem to solve. That would partially be true if you're starting without any prior knowledge of the system, but you know a lot of physics, you can kind of insert that knowledge into your problem, and similar to what we saw yesterday with the example of, or Tuesday with the example of the submarine that got lost, you had this huge space to look into. When you brought in subject matter expertise, or in our case, knowledge of physics, it reduces the space that you need to look into. All right, any questions? To do what for the excited state? To do what for the excited state? Yeah. Oh, the initial state preparation. Yes, you can insert some knowledge. Basically, it gets difficult, more difficult with increasing problem size. So to give you a quick example, in your undergrad, when you see the variational method, you do it with like the potential well. You know a lot of properties of the wave function. You know that the number of nodes increases as you go up in excited state, so you can make a very good guess for the ground state. You know whatever guess for the excited state needs to be an odd function. For example, it needs to have one node. So you're already starting off with better knowledge than if you just do a blind guess. So you can do something similar for excited states. It just gets complicated because the configurations of the spin orbitals that you're mixing gets complicated. Yeah. You can do it as well. It'd be cheating, but you can start as your ansatz, the true eigenstates, and then you'll find that you'll probably converge very quickly.
Yeah, but if you project it one by one, you see 0, 1, 0, 0, because it's orthogonal.
Yeah.
But the energy is still a bit different. So this projection is not really 1 or really 0.
Well, it depends. If you project, you mean like the eigenstates with the ansatz? Oh yeah, then it'll be different. You can use that to compare actually how good your ansatz is. If you, in the cases where you can solve the problem exactly. So I think the biggest takeaway from this, if you forget everything else, is keep in mind that the way that you should do physics is, first of all, remember that you're doing physics, you're not doing math. And secondly, you have both tools at your disposal. You can use your physics knowledge. When you run out of physics, use a little bit of math to take you further. When you run out of that, use a little bit of physics again to take you further, and kind of use that hand in hand to solve a given problem. Use all of the tools that you have, but importantly, as this example illustrates, always keep in mind that you're looking at a real physical system.
How did you know the number of electrons were not conserved?
You look at the eigenstates. Okay. So, we focused over the last few days at applications of quantum computing to estimating energies of simple molecules, but the same idea remains for more complicated molecules. It just gets harder. And ultimately, what you want to do, of course, with that is estimate properties of complicated materials in a sort of computationally aided design of new materials or of drugs or what have you. And that's really what we're looking to do with quantum computers in quantum chemistry. As you know, as you're aware, there are several kind of regimes to the quantum computing industry and quantum computing technology. The current era, roughly speaking, is what has been called the NISQ era for noisy intermediate scale quantum technology. I think this term was first coined in like 2017 by John Preskill. There's some debate about whether that era is over. Some people say late 2023, the NISQ era sort of ended. 2024, there's still a lot of investigation on variational algorithms, but probably in the near future, you're going to see more exploration of algorithms beyond the NISQ algorithms that we saw over the last few days. The next era has a few different names. As I said, at Xanadu, we like to call it the ISQ era for intermediate scale quantum computing. You start removing some of the noise that is limiting the depth of the circuits you can run, the number of qubits that you can use. If you want to know about this, we have a blog post by the head of the algorithms team at Xanadu from a couple of years ago who kind of explored this topic. And then, of course, you have kind of the holy grail of quantum computing, which is the fault-tolerant quantum computing era. So if I can briefly describe some of the characteristics of each one of these. The NISQ era is roughly characterized by hardware that has maybe a few hundred qubits available to you, qubits that are not protected by noise. So depending on the architecture, they'll have finite coherence time, finite fidelity if you make errors in your computations or in your gates. It's also going to affect the accuracy of your system, so you're typically limited to something like less than 1,000 gates, which we're going to look at resource estimation in a little bit. You'll see that even for variational algorithms, less than 1,000 gates is actually pretty restrictive, because remember, you need to run the circuit several times to estimate expectation values. And then on top of that, you need to do it over and over again as you optimize the parameters. So you quickly run out of the number of gates that you can run with noisy hardware. In spite of that, it's been an important era to understand a little bit more the limitations of quantum hardware, the true characteristics of it. We can run simulations like we're running all day long. It's never going to tell you if it's going to work in a real quantum computer. So it's still been an important era. It's allowed groups to explore hybrid algorithms and kind of the limits and capabilities of quantum hardware. The next era is where you're going to start seeing the beginning of qubits that are protected from noise. These are known as logical qubits. Usual estimates that you'll see is a logical qubit will need about 1,000 physical qubits. So you can see the problem is starting to scale very quickly. But what that will allow you to do is start looking at algorithms that go beyond thousands of gates in circuit depth. You're going to need to develop a whole range of new algorithms, so you can explore algorithms that have a higher cost than the variational ones that we've looked at. And obviously, that will start allowing people to explore more complicated systems than just an H2 or H3 molecule. The fault-tolerant era is what we can characterize as you now have hundreds of logical qubits at your disposal, so hundreds of qubits that are robust to noise and errors. You can run algorithms of tens of millions of gates, which sounds like a lot, but it's actually not that much when you look at things like quantum phase estimation, which we'll look at a little bit later today. And this is where, if and when we get there, you'll really start to see this being applied to complex industrial problems, like looking at complex molecules for batteries, for drug development, for proteins. So, of course, we're still relatively in the midst of this NISQ era. This is the realm of these variational algorithms that we've been exploring. One of the big limitations of quantum computers is something called gate fidelity. How many of you have heard about gate fidelity before? Only some of you? Okay, so gate fidelity you can think of as how accurately does your gate perform the operation it needs to operate, it needs to do. So one way of thinking about it is you have some gate V that is noisy. You apply it to a set of qubits that are all in the zero state. You apply the adjoint or the inverse of that gate, and you try to see if you recover the zero state. If you don't, then your gate has a fidelity of less than 1. If you do, your gate has a fidelity of 1. This goes into the amount of error that you can expect from your algorithm when you start working with imperfect gates or with real quantum hardware. Roughly speaking, if you can estimate the average fidelity of a range of gates, of single qubit gates and double qubit gates, you can get an estimate for the percent error as the number of gates increases in your circuit. And just for the sake of illustration, if you look at relatively high fidelity gates, so these are probably by now close to state-of-the-art fidelities in a lot of architectures, you can see that for single qubit gates that have a fidelity of better than 0.001%, once you start getting to about 200 of these single qubit gates, you're getting close to an error of 20%. So it doesn't matter how well everything works, just from your single qubit gates, you've already introduced a 20% error. And we saw on Tuesday the consequences of that, for example, in estimating activation energy or reaction rates. It gets even worse for 2 qubit gates. 2 qubit gate fidelities are typically worse than single qubit gate fidelities. In this example, I haven't taken them to be too much worse, but you can already see that when you get to 200 2 qubit gates, so 200 C0 gates, for example, you're already making an error of 60%, which probably in every application is far too big to be of use. Okay, so that's the reason for the interest in kind of NISQ algorithms, is really to try to limit the number of gates that you have. But clearly, you're going to need error correction to reduce this error and increase the number of gates that you can apply. Any questions about this so far? Good. Okay. So this brings me to a very short segment on kind of ISQ and fault-tolerant algorithms and resource estimation. We're going to look at kind of the godfather of fault-tolerant quantum algorithms for energy estimation. We're going to look at quantum phase estimation and the number of resources needed to do that. So I'm guessing most of you have heard of quantum phase estimation. So all quantum phase estimation is, in principle, is an algorithm that lets you estimate eigenvalues of a unitary. So if you have knowledge of an eigenstate of a unitary, you can estimate its eigenvalues with a quantum phase estimation. The circuit looks something like this. I won't go through it in detail at all. There are several sources for this. But the idea is you have 2 qubit registers. One of them is encoding the eigenstate of your unitary. The other one is encoding the phase information, so the information on the eigenvalue. And as you run through a series of operations, what you get at the output, if you measure the register encoding the phase of your eigenvalue, you'll get a pretty good estimate of the eigenvalue of any unitary that you want. We won't implement this algorithm today. We'll do that tomorrow once we look at how you can implement the time evolution operator. So we'll look at, there's a range of algorithms that have been developed to estimate resources for quantum algorithms. We'll look at a couple of capabilities in Penny Lane for estimating resources for EQE and QPE and compare them. So, if you go to the last section of the notebook, we're going to do resource estimation of the VQE algorithm for water. So still a very small molecule, nothing near what we will be interested in kind of at an industrial level. So we're going to build up the Hamiltonian of this molecule very quickly. Okay, so we have the Hamiltonian. We're going to get all of the coefficients of the Hamiltonian. So remember the Hamiltonian. Right, it's typically, for molecules at least, typically composed of a linear superposition of Pauli operations. These okay, it can be any combination of tensor products of all of the Pauli matrices. So we're going to get all of those values. And then the first thing we're going to estimate, which is not something that we've talked about very much when doing these simulations, is how many shots you need to reach chemical accuracy. If you noticed, we've never specified how many shots to take when we sample expectation values. The reason for that is because we're using a simulator that calculates exact expectation values. That would mean, theoretically taking infinitely many measurements and calculating expectation value. In practice, you of course can't do that. You're paying a company money to access a quantum computer and to run the circuit, so you're going to have a finite number of shots. If you want to know how many shots you need to estimate the ground state energy of water to chemical accuracy, then Okay, so for the case of water, you would need about 5 billion shots to get the ground state energy at chemical accuracy. Remember, a shot is you run through the circuit once. So you can start to see, if you remember the graph I showed you earlier, even for NISQ algorithms, you're very quickly going to run out of the allowance of gates that you can use. And I would say, maybe Marco has a different opinion on this, but you can see why some people believe that NISQ algorithms are going to be of limited use at the end of the day. They're hybrid algorithms. They might run into problems in the classical optimization part. Classical optimization is still a very difficult problem. If you have the resources, you might be better off running an ISC or fault-tolerant algorithm once the hardware is ready for that. No. I would say because there's a lot of interest in NISQ algorithms, and given the state of the hardware in 2017 when this first started, it's difficult to object that. So naturally, there's been a lot of work in trying to reduce the number of measurements you need to take with NISQ algorithms. One of those, for example, is grouping observables that are commuting with one another so that you can measure them simultaneously and actually reduce the number of shots you need to take. So we're going to do something a little different. We're going to group our observables of our Hamiltonian. And now try to estimate the number of shots again. Okay, so you can see we've reduced the number of shots by about half, but it doesn't help you very much. You still need billions of shots to get to chemical accuracy for a simple molecule like water. You can also, if you can afford to not reach chemical accuracy necessarily, you can also see how the error scales or how the number of shots scales as a function of the error that you can tolerate. And this one you can just run as it is. And you can see that for VQE, depending on the error that you have, the number of shots that you need is related to the inverse square of the error. Okay, and these kinds of studies are very important in resource estimation because it gives you a lot of work is going into developing algorithms that require less and less resources, precisely for the reason I showed you before, but also so you can do something useful sooner. You don't have to wait maybe for full fault tolerance. You might be able to do it with just a few logical qubits and a few thousand gates. You can do a similar thing with quantum phase estimation. This one, I won't go into the details of how this is done. You need to compute certain electron integrals, run a double factorization algorithm. The details here aren't super important. What we're going to do here is estimate the number of gates that you need and the number of logical qubits, of non-Clifford gates that you need, and the number of logical qubits to run quantum phase estimation for water. And you can start to see why this need for tens of logical qubits and thousands of gates, if you're doing what I'm going to call canonical quantum phase estimation, which is the very first way that was developed for quantum phase estimation, we're still very far from that. You need close to 300 logical qubits. If you remember the scaling, you need about 1,000 physical qubits for a single logical qubit. And you need, 103 million non-Clifford gates. Okay. Again, keep in mind this for water. We're not looking at anything like a material or a molecule or a biomolecule. So there's naturally a lot of work that has been done and that continues to be done to come up with better ways of doing quantum phase estimation. If you had all the resources in the world, most problems in energy estimation would be solved by quantum phase estimation. We don't have these resources, and we won't have these resources for a long time to come. If you're interested, you can change the basis set. So here we specified a minimal basis set, so the lowest possible number of basis sets that you need. Yeah. Mm-hmm. Yeah. Yeah, it's not, it's difficult to make general statements. It's problem specific, like most things. So yeah, it also depends on the complexity of the optimization problem that you have. Yeah. So if you're interested, you can change the basis to something, to a larger basis set, and you can see how the numbers get bigger. So you can, for example, this 631G is what's known as a Popley basis set. It's just think of it as you're using more terms to specify your state. Let me actually do this so that we keep the number. Maybe before it runs, how do you think the numbers are going to scale? So this is, you can think of it as lowest possible precision. This is going to be a higher precision. So if you remember that diagram I showed you with basis set size and it has like a line going down, if you could estimate, do you think it's going to be twice the number of gates, 3 times the number of gates, 100 times? I don't have the graph, but it is, I would say, close to state-of-the-art precision. Billions, so let's see. So you have about 700 logical qubits, which doesn't sound like a lot, but remember the scaling of 1,000 to 1. So significantly more qubits. And you have about 3 times as many non-Clifford gates. So you're now up to 305 million gates that you would need. So this is lowest possible accuracy. You're already at 1 million. If you want more, you're now at 3 million gates. Okay, so this is a sort of to give you perspective on some of the challenges around quantum algorithm design. Clearly, we need algorithms that need less resources. We need error correction, obviously. And on the hardware side, you still need higher gate fidelities. to kind of realize this promise of quantum computing for quantum chemistry. And I think that's it for today. Tomorrow, we will look at a slightly different problem in quantum chemistry, so quantum dynamics. We'll only talk about trauterization. It's kind of the simplest algorithm to understand, but there's more advanced ones. And then we'll apply, that's going to allow us to calculate the time evolution operator, so e to the I of your Hamiltonian, and it'll let us do quantum phase estimation for a simple molecule. Okay, and that's the plan for tomorrow. Thanks. Peter.